All right, ladies and gentlemen, we're at our third and final question from our summative. So if we take a look at this one, it says that we're identifying if the graph is endo or exothermic. We need to write an equation. We need to label the activation energy on the graph, and we need to discuss what that activation energy is really telling us. So the first thing we're going to do is label that activation energy, which is right up at the top above our delta H value. And we know that this is our activation energy because we know that our activation energy really tells us one thing. It tells us that it's the energy required for the reaction to start. Just anytime we're starting a reaction, sometimes we do need a reaction energy or this activation energy that gets the reaction going, or else if we don't get to that energy peak, we aren't going to have a reaction happening. So now we need to label it this reaction as endo or exothermic, and this one is going to be endothermic because if we look at our reactants versus our products, our reactants are much lower on our energy line than our products are. So now if we determine that, we now need to come up with an equation, and that's the last step here. So our equation we know has calcium carbonate on our reactant side. But that's not all, because if we need reaction or we need energy for this reaction to happen, we're absorbing energy due to it being endothermic. We need energy on that reactant side. So we need a delta H over there to make our CO2 and our CaO. So our carbon dioxide and our calcium oxide. Once we know that, we're actually going to solve for our delta H variable. We know that it's absorbed, which is going to be our calcium carbonate. It's the only reactant. And we look up at our table, we find that value of 1,207.6 kilojoules per mole. We know that on the reactant side, or our release side, our product side, or the releasing of energy side, we have CO2 and calcium oxide. When we find those values on the table above, it's going to be 393.5 plus our 634.9 kilojoules per mole. If we add these two values together, we get 1,028.4 kilojoules per mole. And if we're solving for delta H, we're going to do absorbed minus the released energy, or we're going to do reactants minus products. Either way, we do 1,207.6 minus our 1,028.4. When we do this value, we get our delta H variable to be 179.2 kilojoules per mole. Now, in our equation, we do have to put this value back in where delta H was. So it should now be calcium carbonate as a solid plus our 179.2 kilojoules per mole. And that's going to equal or make or yield our CO2 and our calcium oxide. Once we have our delta H variable, we still need to go ahead and solve for delta G. So we're going to solve for our delta S variable now. In order to do that, we need our S of our reactants, which we know our only reactant is calcium carbonate. And the variable and the value of that is up at the table above, which is 91.7 joules per mole Kelvin. We know that we need our S of our product side, which is going to be our carbon dioxide and our calcium oxide. And if we find those two values, it's going to be 38.1 plus 213.8 joules per mole Kelvin. If we solve for S of our product side, we get 251.9 joules per mole Kelvin. And to find our delta S value, we're going to take our products minus the reactants for this one. So delta S is going to equal 251.9 minus 91.7. When we solve for this variable, we're going to get a delta S to be 160.2 joules per mole Kelvin. Once we do that, we can now solve for our delta G variable. So now we're going to list our givens. Our delta H is going to be that 179.2 kilojoules per mole. Our delta S is going to be that 160.2 joules per mole Kelvin. And we know from the original problem that our temperature is going to be 313 Kelvin. Once we have all of this, we can take a look at those units just of energy real quick, and we can see that kilojoules and joules do not match up. We need to convert one or the other. Again, I'm just going to convert the kilojoules to joules just because that one was on the paper first. So now we're going to convert using our railroad tracks. I'm going to place that 179.2 kilojoules per mole in our first column of the railroad tracks. We know that 1 kilojoule needs to go on the bottom. We need to put our 1,000 joules up top because that's our conversion factor. When our kilojoules cancel out, we get a value of 179,200 joules per mole for our delta H variable. Now, if we're solving for our delta G, we solve delta G equals delta H minus T delta S. When we do this, we plug in our 179,200 joules per mole minus our 313 Kelvin times 160.2 joules per mole Kelvin. We'll solve for our T delta S first, so we'll rewrite our delta H value minus our T delta S, which is 50,142.6 joules per mole here. Once we solve for our delta G, we should get a value of 129,057 joules per mole. Once we turn it into significant figures, because I know that's all of your favorite things to do, we should get a value of 129,100 joules per mole. If you wanted to convert that to kilojoules per mole, or if that's what you solved for, you should have gotten an answer of 129.1 kilojoules per mole. If you have any other questions, remember to email, send reminds, ask Canvas questions, whatever you need to do. Have a wonderful rest of your night and a great spring break.